Hello, welcome back to the second course in physics. And today we will start discussing another topic which is related to the time effects in electromagnetics. And to begin with, we will be talking about electromagnetic induction. The contents of this lecture will include some general introduction, and then we will describe some of the experiments which led to the basic findings in this field. These experiments lead to Faraday's law, and we will describe how this law explains and interprets the experimental findings. Then we will define or we will state Lenz's law and see also how consistent it is with the experimental observations. And then we will talk about the induction and the energy transfer. And finally, we will be talking about the eddy currents produced in sheets moving in a magnetic field. As a general introduction to the field of induction, we mention historically some historical facts that back in 1831, Michael Faraday in England discovered a very important discovery, that the action of changing magnetic induction can induce or produce an electromotive force which causes current to flow in a closed circuit. This was an important finding and a turning point in the field of electromagnetism. The discovery opened a new way for the practical conversion, practical applications in the sense of conversion of mechanical power into electrical power, as in the electrical generators, and also has applications. These observations have applications of electrical power, changing electrical power into mechanical power in the case of electrical motors, for example. So it has very important technological and industrial applications. This discovery was the essential starting point, as we just mentioned, for the understanding of the electromagnetic phenomena. These interdependent phenomena which arise from the time dependence in the electric and magnetic phenomena. It just turns to couple the electrical phenomena and the magnetic phenomena. This coupling occurs due to the time dependence of the electric and magnetic fields, or the sources of these. And now we discuss some of the basic and early and most important experiments which led to the most important statements or laws in this field of electrodynamics. In experiment 1, we have a circuit with changing area that is placed in a uniform magnetic field. So we have a magnetic field, we have a circuit the magnetic field is uniform, and we assume that the magnetic field is perpendicular to the area of the circuit, and the circuit has a changing area. And the way to change the area of the circuit is that if we have some sort of rails, two rails, which are connected with an ammeter connected with it, and we close the circuit by putting a movable wire or rod, conducting rod, this one. So if we move the conducting rod or the wire to the right, for example, as the figure shows, the area increases, and vice versa. If we move it to the left, the area decreases. So that way, moving the rod will induce a change in the area of this circuit. So in experiment 1, with the area changing, it was found that as the movable wire AB moves to the right, for example, with velocity v, current appears in the circuit just by moving this wire. This is the result of experiment number 1. And there is another experiment, experiment number 2. In experiment number 2, we have a rigid circuit now, a circuit that does not change the area, but instead of in a uniform magnetic field, we have this rigid circuit placed in a varying magnetic field. So we change the conditions. So here we have a rigid circuit, C1, does not change area, but the magnetic field can vary across this area. And it was observed that there is an electric current in C1 that starts flowing only when the magnetic induction across the rigid circuit varies. That means if we vary the current in C2, because if current is flowing in C2, then it produces magnetic field, as we have discussed in the previous lecture. And this field, if the current in C2 changes, then this field that crosses the area of C1 will be changing. And in that case, we observe an induced current, a current that starts flowing in C1 as a consequence of the changing magnetic flux that crosses this rigid circuit. This is the result of experiment 2, second experiment. And so the magnetic induction across the circuit can be varied by varying the current in circuit C2, as we mentioned. But there are other ways of changing or varying the induction across the circuit that lead to exactly the same results. For example, if we have the rigid circuit stationed in space, like in this loop, as in this figure, suppose that this loop is the circuit, C1, and if we approach this loop by a bar magnet, then since the field lines of the bar magnet are fringing, so as we approach the magnetic field, as we approach the loop, the magnetic induction or the magnetic field will change across the loop. So that is another way of changing the magnetic induction across a rigid circuit. And also, in this case, we see the same result. Current starts flowing in the loop as we approach it by bar magnets. There is also still another way of changing the magnetic field or the magnetic induction across a rigid circuit, just keeping in mind that because the magnetic induction is a vector, the ways to change the magnetic induction is not necessarily to change its magnitude. Since it's a vector, we can change the magnitude, and that means changing the magnetic induction. We can change the direction of the magnetic induction, even if its magnitude is uniform, is the same, if its magnitude is the same. But if we change the direction at which it crosses the loop, then that means changing the induction. So if we have a uniform magnetic field, for example, and we rotate the loop in the field, then rotating the loop will see different directions for the magnetic field as it rotates. Thus, the magnetic induction will be changing across the loop. So this is also another way of changing the magnetic induction across the loop. And again, if we rotate the loop in a uniform magnetic field even, we also see similar effects. The current starts flowing in that loop. These are the observations which are results of experiment number 2, which is changing the magnetic induction across a rigid circuit. And now experiment number 3 is concerned with another set of conditions, which is a rigid circuit. The whole rigid circuit is now moving in a static magnetic induction. So this is a rigid circuit, C1, and C1 as a whole is moving. Now, the area of the circuit is not changing, but it's moving across the space. And now, if the magnetic induction is non-uniform, the results of this experiment is as follows. If the magnetic induction is non-uniform, meaning the magnetic induction changes from point to point in space across the circuit C1, if that is the case, then we see current flowing in C1 as the rigid circuit moves across the non-uniform field. So a rigid circuit moving across a non-uniform field would produce current in C1, in that rigid circuit. However, another observation of this motion of a rigid circuit in a field is that we notice that if the magnetic induction is uniform, if it's exactly the same in magnitude and direction in space, and if we move this rigid circuit without rotating it, of course, just move it translationally across the field, no current will be produced in C1. This is the finding of this is the observation of experiment number 3. A loop moving near a bar magnet produces exactly the same effect, because this figure shows a similar conditions to the ones explained a little while ago, because we have here a rigid circuit, which is the loop, and the rigid circuit is moving in space. If the field is non-uniform, as the field produced by a bar magnet in this case, this field is non-uniform. So if we move the circuit across this field, then we will find, or we will observe, current flowing in this loop. So this is these are experimental observations, and now we move to explain these experimental observations, and this leads to Faraday's law, that was a result of his novel work in this field. And this law gives an interpretation for all of these experimental observations. And the interpretation of all these observations is that an induced current appears in a circuit if the magnetic flux changes across the circuit. Now, just an insight to the experiments that we have done, the 3 experiments. In each case where we have observed current flowing in the circuit C1, in each case, if we go back and check the conditions, we notice that in each case, the magnetic flux was changing across the area of the circuit. How? How was it changing? The changing or the change in the magnetic flux across a circuit can be done by different ways. Like, for example, if we have a magnetic induction, if it is even uniform, constant in direction and magnitude in space, but we change the area of the circuit, then changing the area would change the flux, because the flux is simply the magnetic field times the area that it crosses. So changing the area would produce change in the magnetic flux, and that is what was done in experiment number 1. And in this case, we saw a flow of current in the circuit. We can change the magnetic flux by changing the magnetic induction across a rigid circuit. The rigid circuit has a constant area, but if we change the magnetic induction now within that area, since again the flux is magnetic induction multiplied by area multiplied by the angle between them, then changing the magnetic induction itself would produce a change in the magnetic flux across the area. And that was done by experiment number 2. And third, if we move a rigid circuit across a non-uniform magnetic field, now the rigid circuit moves from one point in space to another, experiences different magnetic inductions at the different points in space. So as it moves, the magnetic induction would change as it moves, introducing a change in the magnetic flux. So this is another way of changing the magnetic flux across the area, and that was done by experiment number 3. So we notice that in all the experiments that we have encountered, in each case, we have a changing magnetic flux by one way or the other. And all of them, in the case of changing magnetic flux, led to the induction or the production of a current that flows in the loop as a consequence of the changing magnetic flux across the loop. Thus, the induced electromagnetic force, which drives the current across the loop in a circuit, is given in terms of the time rate of change of the total magnetic flux passing through the circuit. This is the only way to interpret the results of the 3 experiments. That there is an electromotive force that arises in the circuit, which is proportional to the time rate of change of the magnetic flux across the loop, because it is a consequence. The current is a consequence of the change of the magnetic flux. The faster the magnetic flux changes, the stronger is the current, or the bigger is the current. And this statement is stated in Faraday's law mathematically, that the electromotive force epsilon that is induced in the circuit is equal to the time rate of change of the magnetic flux across the circuit with a minus sign, and the minus sign is will be discussed or will be elaborated more in the near future. This is just to be consistent with the experimental observations, and to be consistent with another law that we will mention in a little while, which is Lenz's law. And now let's use this Faraday's law and see how does this law explain the experiments one by one. For example, if we pick experiment number 1, the magnetic force on the free charges in the moving wire, we have in experiment number 1, remember that we have the wire AB is moving, and as it moves in the magnetic field, we know that it experiences a force. And the force on a charge, we remind ourselves that the force on a charge, on a moving charge, is equal QV cross B, where V is the velocity of that charge. And since the moving wire or rod AB carries free charges, it's a conductor, then it experiences force. And this force that it experiences, QV cross B, it's in the direction of V cross B, which is in the direction from B to A. This force acts on the charges, on the free charges, so it drives the charges to move, positive charges, to move from B to A. Current, that means, flows from B to A, or negative charges moving from A to B. So the current flows from B to A because the force will be directed from the force acting on a positive charge will be directed from B to A from this law, QV cross B. So then that means in this wire we have a force that is acting from B to A. And this force is associated with an electric field. The force on the charge divided by the charge is equal to the electric field. So there is an electric field that is set up in that moving wire, which is simply V cross B. That is the electric field that is set up in the moving wire. So that means moving the wire would introduce this electric field. So it'll be like a battery. This wire will be like a battery. So the motion produces an electrical source in a way. And the induced electromagnetic force, this is the wire, the moving wire. There is an electric field that is directed from B to A, as we mentioned. And since it is constant, the electric field, because the velocity of all the parts of the wire is constant, then the voltage difference across this wire from B to A is simply the electric field times the length of this wire, which is simply V cross B, that's the electric field, as we mentioned a little while ago, dot L, which is the length of the wire with the direction of the current applied to it. And then this can be changed a little bit. If we just change V cross B, instead of V cross B, we write B cross V. So we will have a minus sign here, and dot L. So this is the same as this, but changed, the order of V and B are changed. So epsilon is equal to minus B cross V dot L. This quantity B cross V is dotted into L, which is equal to minus B. Now we use this identity that B cross V dot L is equal to B dot V cross L. So this result is B dot V cross L. And we know that V, if we consider that this direction of motion, the direction of motion of the wire, if we consider it the x direction, then V is simply dx by dt. Dx by dt is V. And we notice that L, the length of the wire, times dx is the area that is covered by time dt. So this gives epsilon is equal to minus b times dx by dt cross L. Dx cross L is the area that is made by the motion. It's the distance in the direction of motion times the length, with the cross product giving sine 90 degrees in between, because the direction of the wire. This is a general formula, of course, but in the example that we are encountering, V is perpendicular to L, so the angle between them, V times L times sine 90, which is simply 1, V times L. So V times L is simply dx times L by dt. Dx times L is the area, dA, by dt, dA by dt. So we have epsilon, the electromotive force that is produced in the wire as the wire moves, is equal to simply minus b times dA by dt. And because b is constant, so we can apply the time derivative to b times a, because b is constant simply. So b dot a is simply phi, the magnetic flux. So epsilon is equal to minus d phi by dt. This is the Faraday's law that we have just stated a little while ago. So as you notice, we can look into the problem as being electromotive force produced, and we can produced by the changing flux. So there is an electromotive force that is a result of the flux, and that result, we arrive at this result from the basic concepts that we have learned concerning the force that a magnetic field exerts on a moving charge. And we arrive at Faraday's law, which is correlating this electromotive force with the flux change in the circuit. So this is as far as experiment number 1 is concerned, and experiment number 1 is an example of a simple electrical generator, because here we are converting the mechanical motion. We are moving a wire, and this motion of the wire is producing an electromotive force in the circuit. It produces electromotive force, it produces current. So this is an example of the electrical generator. If a current flows in the circuit, the wire moves to the left. This is just reversing the or looking at a problem from another way, just considering the forces of interaction between a wire or charges and between the magnetic field. If we assume that this circuit in experiment number 1, instead of moving the wire and producing electromotive force, if we just reverse the situation, if we have an electromotive force that is driving current along the circuit, and the rod BA is free to move, then the magnetic field will be exerting force on, of course, it exerts force on all the wires in the circuit, but all the wires are rigid except the wire AB. This is movable, and the force exerted on the wire AB will be to the left. So the wire AB will move by itself to the left. And this is an example of a motor where we are having an electric power electric energy, and this electric energy is converted into motion, is converted into mechanical motion. The current produces mechanical motion, and this is a simple example of a motor. And now let's discuss experiment number 2 in the time varying magnetic induction. Time varying magnetic induction we have in experiment number 2, and the circuit is rigid. And if we consider Faraday's law, epsilon is equal to minus d phi by dt, and then this is the electromotive force. And now if we integrate the electric field around the loop C1, this is what the electromotive force epsilon is. Of course, epsilon electromotive force is introduced in the circuit. So epsilon is simply E dot dl integrated around the circuit C1. That is what epsilon is. So we're just substituting for the value of the electromotive force. And that is equal to minus the integral over the surface area of the loop, dB by dt dot dA. The loop is not changing in area, but the magnetic induction is changing. So d phi by dt attacks only the magnetic induction. Notice that around a loop in the static case, electrostatic case, E dot dl is equal to 0. If we start from one point and we make the integration E dot dl and we go back to the same point, in general, this is equal to 0. But in the dynamic case, where there are time effects, E dot dl around a closed loop is not 0, and this is due to the time effects only. So just keep in mind the time effects and what they can do. That they can produce time effects on magnetic phenomena, we could produce electrical phenomena, and vice versa. And this is the field that we will be talking about in the next few lectures. Now, we use Stokes' law applied to E dot dl, and we convert E dot dl into a surface integral. So E dot dl is equal to curl A dot dA integrated over the surface. This is equal to minus the integral over the surface area of the flux, dB by dt dot dA. And the only solution for that is if curl E is equal to minus dB by dt. If curl E is equal to minus dB by dt, then this is a correct statement. So notice this relation, and keep in mind the electric field produced by induction is non-conservative, because E dot dl, as we mentioned, over a closed loop is not equal to 0. So the electric field that is produced by induction, which is an effect of time, is not conservative. The electric field due to electrostatic charges is, of course, conservative, because E dot dl integrated over a loop is equal to 0. And experiment 3, in experiment 3, the electromotive force is induced. If we assume this motion of the rigid circuit, the induced electromotive force appears in wires AB and CD only, because it is here where the velocity is perpendicular to B and produces a force in the third dimension. In the cases of CB and DA, these wires, the electromotive force is lateral, and it does not introduce any driving force of the charges. So it does not do anything. Now that means in the wire CD, we have an electromotive force as a consequence of the motion. If we consider, as we did in experiment number 1, if we consider the force that is exerted by the magnetic field on this moving wire, CD, and the force that is exerted on this wire, on the charges in this wire, AB, as it moves. So we have an electromotive force in AB and an electromotive force in CD. And these electromotive forces, if we take V cross B, the direction of them look like this. So they are in opposite direction. One of them is driving current counterclockwise, and the other one is driving current clockwise in the circuit. And if these two electromotive forces are equal in magnitude, then there is no current that flows. And the way that these are equal is that if the magnetic field is uniform all over the space. So the magnetic field that is crossing in the region of the wire AB is exactly the same as the magnetic field in the region of CD. So the force is exactly the same, the electric field is exactly the same across these two wires, and then the electromotive force is exactly the same. And thus we will have two batteries with opposite directions, and the result is a zero current in the circuit. However, and that's why if we have this rigid circuit moving across a uniform field, we'll observe no effect, no current. But if the magnetic field is varying from one point to another, so in the location of one wire, the magnetic field is different than the magnetic field in the location of the second wire, then the electromotive force in the two wires will be different, and that will produce an induced current in the circuit. This is an explanation. Now we go to Lenz's law. Lenz's law is actually concerned with the direction of the produced electromotive force. And Lenz's law states that an induced current has a direction such that the magnetic field due to the current, to the induced current, of course, opposes the change in the flux or in the magnetic field that induces that current. So, as we are thinking of the induced current, we think, what is the effect that's causing it? The induced current will oppose that effect. That is simply Lenz's law. That's why the negative sign that appears in Faraday's law. And now we can explain we can explain this law by considering a number of examples. For example, if we have this loop, and this loop is nearby a bar magnet, and this is the N pole. The red pole is the N pole of the bar magnet. So the magnetic lines, field lines, are going out of this end and crossing the loop. So if the bar magnet moves away from the loop, then the magnetic induction across the loop and the magnetic flux is decreasing in the direction to the left. It's decreasing. So there will be an induced current that appears in the loop. In the loop, there will be an induced current, and this induced current will be in the direction such that it increases the magnetic induction, because moving the bar magnet away will decrease the magnetic induction in this direction. So we will have a current, an induced current, such that it increases this magnetic induction. It opposes the effect. The effect of getting far away from the loop is decreasing the magnetic induction. The current, the induced current, will increase the magnetic induction in that direction, opposing the effect. And this is just the opposite. If we approach the loop with the bar magnet, then the induced current will be in an opposite direction to oppose the increasing magnetic induction in the loop. And now if we have, for example, a circuit, this circuit C1 will have no current when the switch S is open. Now, if we close the switch S, then there will be magnetic lines introduced by the magnetic induction produced in C1, and that magnetic field will start introduced in space, and it will cross this loop. The field lines will be like this and crossing the loop. As a consequence of the increase in the flux in this loop, then there will be an induced current in the loop that decreases the flux in this direction. That means the flux of the magnetic induction due to the induced current will be upward, opposing the downward magnetic induction that is produced in the loop. So this is another let's see, for example, we can make an application. These are two loops nearby each other, and we say if current C1 increases, then a current in C2 will be produced in this way. You can convince yourself using Lenz's law. And if the current in C1 decreases in this direction, then an induced current in C2 will be induced in this direction. And now we can talk about induction and energy transfer. Now, if we have a rigid loop that is moving in a region of magnetic field, the magnetic force on the loop is the magnetic force that is acting on this line of the loop. And the force is IL times B. L is the length of that wire, and and B is the magnetic induction. And now, as we move, there is an induced current, and the induced current will be affected by the magnetic induction itself by this force. And the power is simply equals to this force times the velocity. And look at the force. It is opposing the effect. The effect is to pull the loop to the right. Then there is a force that is exerted on the loop to the left. This is a consequence of Lenz's law. The induced current opposes the effect. And in a similar way, we can look at a sheet of metal. If it is pulled in a magnetic field, eddy currents will be produced in this direction that is shown to pull or to oppose the motion of the sheet and to stop it from motion. And this is also a consequence of Lenz's law. And this illustrates the principle of what we call the magnetic brake. At this point, I would like to end my lecture, and thank you for your attention.